Okay, what about the shape of the sampling distribution of a sample mean, SDSM, when the sample is not taken from something normally distributed, right? Does the sample size matter? Does the sample size matter? Yes. That sample size needs to be greater than or equal to 30, right? Does this have a name? Yes. It is given the name the central limit theorem, right? Which you can abbreviate as CLT. Okay? So if the sample size is greater than or equal to 30, and this is a general rule. There will be some times that this will need to be much larger. There will be some times that it'll work if it's smaller, but this is our general rule. So if the sample size is greater than or equal to 30, then our sample distribution of sample means is going to be approximately normal, with some mu and some sigma over the square root of n. Okay? That's if I happen to know mu and I happen to know sigma. Okay? Otherwise, we're going to have a different approach. Okay, so let's put this into practice. All right. Suppose a large number of texts sent during a typical day, randomly selected high school students, are right skewed. Well, look at this. Right skewed means not normal. Okay? And here is a mean, and there is a standard deviation. Assume that the students are typical texters and that you select 50 students from the school. So n is equal to 50, so therefore n is greater than or equal to 30. So I can use the central limit theorem. Okay? So calculate and interpret the standard deviation of the distribution of x bar. So sigma of x bar is going to equal sigma over the square root of n, which is 35 all over the square root of 50. That is approximately 4.95. Okay. Now we do know that x bar is approximately normal with mu sub x bar sigma x bar. Okay. And that's because we have a big enough sample size. So interpret this. Okay. This is a very, very, very important interpretation. So therefore, in random samples of size n equals 50, the sample mean number of texts typically varies from the true mean by about 4.95 texts. Okay. Remember that you want to always include context. All right. What is the context here? The sample size, and that we're talking about number of texts. So in a random sample of size n equals 50, context, the sample means number of text, context, typically varies from the true mean by about 4.95 texts, context. Very, very, very important that we include context always. Right, and once again, because our sample size is large, greater than or equal to 30, we can use the central limit theorem that lets us say our sampling distribution of sample means is approximately normal, with some mu sub x bar and some sigma x bar, where sigma x bar is sigma over root n. Okay? So, you'll notice that our next problem is going to look very similar in structure. Okay? What is the probability that these students have sent more than a total of 1,000 texts? Okay? if total is greater than 1,000, then x bar must be greater than 20. Right? Why? Because 50 times 20 needs to be more than 1,000, and there was 50 of these students. Okay? Now remember, x bar is approximately normal with the mean of 15. Why mean of 15? Mean of 15. And the standard deviation, 4.95. Why 4.95? That's what we calculated for the mean of the sample distribution. And we want to know the probability that x bar is greater than 20. We need a z-score, which would be 20 minus 15 all over 35 over root 50, which is about 1.01. So I want the probability that z is greater than 1.01, which is the same as 1 minus the probability that z is less than 1.01. I wrote that incorrectly, 1.01. Okay. Which, if I use my calculator or I use my table, that's 1 minus 0.8438, which is about 0.1562. Right? So there is about a 15% probability, right, 15-16% probability that the student sent more than a total of 1,000 texts in the last day. Right? This should start to look familiar. What's my notation? Right, set it up, calculate the z-score, rewrite the notation, rewrite again in terms of less than if you have to, make the calculations, get the value, set it up. Okay? Very, very important.